Now that you've proven the laws of sine and cosines, it's time to use them. It's time to apply them to situations in the real world like vectors, forces, surveying, all kinds of things. Let's take a look at the law of sines. We use the law of sines for any kind of triangle, and a triangle can be not just a physical triangle, but a triangle of forces, of vectors, and many other things. The law of sines states that the ratio of the side to the sine of the angle opposite that side is equal on all three parts of the triangle. You can put the lengths on top and the sines on the bottom, or you can use the reciprocal of that because they're both true. Generally, if you're solving for an unknown side length, you're going to put the lengths on top. If you're going to solve for an unknown angle, you're going to put the sines on top. Now, you're going to use the law of sines in situations where you have 3 dimensions of a triangle and you need to find the other 3. But the specific situations you're going to want to use the law of sines in are the 3 that are listed here. First, angle, angle, side. I've got 2 angles on one adjacent side. Angle, side, angle. I've got 2 angles and their included side, and side, side angle, where we have 2 sides and an unincluded angle. Now, you're going to see that SSA situation creates what's called an ambiguous case because it could create 2 triangles, 1 triangle, or no triangle, depending on the situation. So let's look at an example. You're given a triangle with an angle of 70 degrees and 80 degrees and a side opposite the 70-degree angle of 12 centimeters. Find the measures of the third angle and the other 2 sides. Just the convention that we've been using, angles are named with capital letters, and the sides opposite them are named with that same letter but in lowercase. So here's a picture of the triangle ABC, and notice this is an angle side situation, so we're going to be able to use the law of sines. Hopefully we have at least one pair of angle and opposite side. Well, we know first of all that the angles in a triangle total 180 degrees, so the third angle has to be 180 minus those 2, which is 30 degrees. So let's set up the law of sines to find the unknown sides. To find side B, we're going to say 12 over 70 degrees equals B over the sine of 80 degrees. And if we're going to solve that for B, we're going to multiply both sides by the sine of 80 degrees. And we wind up with 12 sine 80 over sine 70 is our answer. And that works out to be approximately 12.6 centimeters. So now we know side B, we need to find side C. And I'm going to recommend that you keep using the ratio of sides that you know in case you made a mistake finding the other side. So to find side C, we're going to go 12 over the sine of 70 equals C over the sine of 30 degrees. Solving it for C, you're going to get 12 times the sine of 30 degrees over the sine of 70 degrees, and that works out to approximately 6.4 centimeters. So now we know all the parts of this triangle, all the sides, and all the angles. Now let's look at another situation with angle, side, angle. You're given a triangle with angles of 115 degrees and 30 degrees, and a side that's included between the angles of 30 centimeters. Find the remaining measures within the triangle. So this is an angle, side, angle situation. And we don't, at first glance, have a side and an angle opposite first, so let's try to find an angle, especially angle A, so that we can at least have one pair of angle and opposite side. Well, again, using the triangle sum rule, since the sum of the angles in the triangle have to be 180 degrees, angle A must be 35 degrees. Once angle A is set up at 35 degrees, we can set this up as a ratio of sides to the sine of the angle. So this A over the sine of angle A, 30 over the sine of 35 degrees, is equal to find B, for example, B over the sine of 30 degrees. We multiply both sides by the sine of 30 degrees, and we're going to get B equals 30 times the sine of 30 degrees over the sine of 35 degrees. And that works out to approximately 26.2 centimeters. So we're getting closer. Now we can use the law of sines again to find C. And again, I'm going to recommend you stick with the pair that you know. 30 over the sine of 35 degrees, A over the sine of angle A, has to equal C over the sine of C. So C over the sine of 115 degrees. When we multiply both sides by the sine of 115 degrees, C is going to be 30 times the sine of 115 degrees over the sine of 35 degrees, which works out to 47.4 centimeters. So now you've got it. Now, just as a little side note, remember to use the law of sines whenever you're given two angles in one side, because you can always find that third angle, which then can allow you to use the law of sines, which is simpler than using the law of cosines. All right, now let's look at situations where the law of cosines needs to apply. And there are two basic situations that the law of sines can't help us with, that the law of cosines is necessary. Side, angle, side, and side, side, side. Angle, angle, angle can result in a lot of different triangles because the triangles can be dilated or expanded. So you cannot really use angle, angle, angle at all. We're going to use the law of cosines for side, angle, side, and side, side, side triangles simply because we can't use the law of sines on them. There isn't a pair of angle and opposite side in either of these two situations. We just don't have enough information. Now, the law of cosines is more complicated, so we will only use it when we need to, and then we can revert to the law of sines once we have the information we need. You'll recall from proving the law of cosines that the law of cosines states that c squared equals a squared plus b squared minus 2ab times the cosine of c. And what that means again is, if we want to find a side, the side we're trying to find squared is equal to the sum of the squares of the other two sides minus 2 times the product of those two sides times the cosine of the angle opposite the side we're trying to find. And that pattern repeats itself for any of the three sides and angles. And we use this to find missing sides and angles, and then we're going to use the law of sines after that. Let's look at a side angle side situation. Now always label and draw the triangle to help visualize what's going on. And here's the triangle where side B is equal to 1, side C is equal to 3, and then side A, opposite angle A, is unknown. Angle A is 80 degrees. This is a side angle side situation, and we must use the law of cosines first here to find side A, simply because we don't have a pair of angle and opposite side. So we're going to be trying to find that opposite side for the angle that we know. And that's always a good place to start with the law of cosines. So we're going to set up and use the law of cosines formula that works for A. A squared equals b squared plus c squared minus 2bc cosine A. So the one side squared we're trying to find is equal to the sum of the squares of the other two sides minus 2 times the product of those sides times the cosine of the angle between them. So let's set that up. Since b is 1 and c is 3, we're going to plug those in. 1 squared plus 3 squared minus 2 times 1 times 3 times the cosine of the angle between them, 80 degrees. Make sure you're in degree mode in your calculator. So when we add up all those things, we get that a squared is approximately 8.96. Now, a very common mistake on the law of cosines is forgetting to take the square root. Don't forget that. This is just a squared. You have to take the square root to actually find side A, and it is 2.99. So now let's put that 2.99 onto side A. Now we have an angle pair, an angle side pair, and so we can use the law of sines. So we know that the sine of 80 degrees over 2.99 is going to equal the ratios of the other sines to their sides as well. Let's do C. It's equal to the sine of C divided by 3. Now notice I put the sines on top because we're trying to find an angle here. The sine of C then, if we multiply both sides by 3, is equal to 3 sine of 80 degrees divided by 2.99, and that is equal to 0.9881. Now we've got to take the inverse sine of 0.9881 to find angle C, and angle C is 81.15 degrees. Make sure you're in degree mode. Well, since we know that C now is 81.15 degrees, we don't need anything other than basic geometry to find angle B, because we know the sum of the angles still has to be 180 by subtracting out those other two angles. Angle B is 18.85 degrees. So we've used the law of cosines first to kind of break the stranglehold side angle side had on us. And once we did that, we could easily use the law of sines and then basic geometry to find the other parts. So let's do another example that's a side situation. Let's draw a picture. Side A is 5, side B is 8, and side C is 9. Side, we don't have any angles here at all. We're going to have to use the law of cosines to get one of those angles. Once we crack the code, though, and get one of those angles, the rest of it falls into place with the law of sines. So let's use the largest side first to find the largest angle first. Reason for this is this relieves that case of ambiguity that can sometimes occur with large angles, that ambiguous case. We're going to do side C first. Again, this triangle's not drawn to scale, that doesn't matter. So C squared equals A squared plus B squared minus 2AB cosine C. So now we're going to actually find an angle here and set that up. So C squared, that one side squared 9, is equal to the sum of the other two sides, which we know, 5 squared and 8 squared, minus 2 times the product of those sides, times the cosine of the angle between them, this C that we don't know. So 81 equals 89, the sum of those two squares, minus 80 times the cosine of C. So the cosine of angle C is equal to negative 8 over negative 80. You've moved the 89 to the other side, you get negative 8. You divide both sides by negative 80. And so a cosine of C is 1/10. Therefore, we have to take the inverse cosine of 1/10 to find angle C. And that is approximately 84.3 degrees. Now that we know angle C is 84.3 degrees, we have an angle side pair, and the rest falls into place very nicely. Now so we can use the law of sines. Again, we're trying to find angles, so we're going to put the sines on top here. So we're going to set it up as the sine of 84.3 degrees over 9 equals the sine of B over 8. So 8 sine of 84.3 over 9 equals the sine of B. After you've multiplied by 8, you get this. So B, therefore, will be the inverse of 8 times the sine of 84.3 over 9. That's going to be approximately 62.2 degrees. Let's put that in our triangle. Now we can use basic geometry to find alpha, or A, that third angle. Alpha is going to be 180 minus the other two angles. It's going to be 33.5 degrees. And now we solved our triangle. Notice how we went after the largest angle first. So that's how you use the law of sines and cosines to solve any kind of problem involving any kind of triangle.